Okay, so we're moving on to chapter 3, which is solving differential equations by power series. So far we've solved first order, second order, and higher order, right? 3, 4, and so forth, differential equations, which is great, right? We've been using our methods in chapter 2. But unfortunately, there are some differential equations that we can't solve using the methods we've been using. So we have another method, which is using power series. So you should have seen power series in calculus, but I'm going to go ahead and just review some of the basics of power series. So let's start off with, review our power series, right? What a power series is. That's an E. Okay. Sorry, that noise is my coffee. Uh, so power series, right, are often infinite, sums of terms. So here's an example. So we are finding our solution, right, to a differential equation, which we've been calling y. And this is going to be equal to the summation of Cn x to the n, where n goes from 0 to infinity. You might have seen some books, or maybe in calculus, they call the term an. Here they're using Cn. If you want to use an, that's fine. Basically, what this means, so this is your power series, right? It's a sum. So here, right, n equals 0, right? The infinity sign on top, right, of the sigma just indicates that, right, n goes from 0 to infinity. Here, Cn and x to the n are constants. And let's see, what else can we say? This is basically a shorthand of writing the following. So if n is equal to 0, then we have C0, x to the 0, plus, when n is 1, we have C1, x to the 1, right? So if n is 0, if n is 1, plus if n is 2, we get C2, x2, and so let's write n equals 2, right? We can go ahead and write if n is 3, C3, x to the third, and again, n equals 3. And I can keep going, right? But I'm just going to go ahead and write plus dot, 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 right? That's what we have. That's why this is called an infinite sum, because the sums, right? They're infinite sums, and we're going to infinity. Some of these some power series are finite, but in our case, ours are going to be infinite series. The only trouble with with this infinite expansion, of course, is that it might diverge. So remember from calculus, power series either diverge or converge, and I'll go ahead and make sure to do some examples of that. But again, this is we're going to be using, right, this notation, but if you ever get confused on what these terms look like, I mean, you're more than welcome to expand them, which is fine because I want you to understand what you're working with. So this is the type of power series you're going to be working with. I did want to mention our this part here, our x to the n. We can have okay, so let me just go ahead and write it. If y is equal to, I'm allowed to have, right, the summation, right, n is going to start at 0 again to infinity, Cn, but I can have, and I'll go ahead and write C, right, so here I have an extra, right, minus C. I mean, in this case, my C was 0, but I mean, I'm allowed to have this power series as well. And then you would do the same thing. You would substitute, right, C0 x minus c to the 0 plus c1 x minus c to the 1 plus c2 x minus c squared plus dot, dot, dot. We can even, I mean, this is just 1, so all of this would just really be C0. And actually, the top part, this guy would actually be C0 as well, because x to the 0 is equal to 1. So this guy is a power series in X, okay? And this guy is a power series in X minus C. So maybe so this is a power series in X minus C, and then this guy is a power series in X. And of course, every general property of power series in X, right, can be converted to this general property of power series in X minus C by literally just replacing it. Now let's quickly just talk about the power series that converges, just a general what happens here with this power series. So we started with the summation of Cn x to the n, right, as n equals 0. Now, this specific power series, excuse me, in x, right, actually converges, right, on some interval, provided that we have a limit. So remember, this guy is really the limit, right, as some maybe capital N approaches infinity, right, because it's not the same thing as our little n, of our power series. So all the way to n, Cn x to the n, right? So the limit exists here for all, right, for all x in I, right? And so this is defined on I, and we call this power series, so in this case, right, our f of x, right, our function, is our Cn x to the n, right, where n equals 0 to infinity, right? This is called a power series representation right, of the function f on I, right? And this guy was our y, but we know that y is a function of x. Now, there are a lot of power series representations, especially of elementary functions, right? Functions that you should be familiar with from calculus. And I encourage you to write, so if you look on page 125 of your book, instead of me just writing all of this out, look on page 195, right? So this is my kind of introduction to this section, to power series especially. And you'll see on page 195, right, there's, e to the x can be written as a power series. For example, we have x to the n over n factorial, right, n equals 0 to infinity. Cosine of x, right, can be written as a power series, dot, 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 sine x, and so forth. These are very important power series that you should, again, be familiar with. So please make sure to look at that, and I will do some more examples, or I'll start the examples and a couple more explanations in the next video. And I did want to say one more thing. Okay, so also in summary, right, we're working with power series, right? So a series is just a summation, right? And the summation has powers, right? So hence the name power series. Okay, I think that's about it. If you have any questions on this video, please just send me a message, and I'd be more than happy to elaborate on a specific part if you'd like.